Welcome to a tutorial on the 8085 microprocessor. And this video we're going to talk about the stack pointer and the program counter registers. Okay, so as I promised back in the previous tutorials, I think you'll remember this figure on the left. Okay, because if you don't, then I would tell you that this is obviously the 8085 microprocessor's RAM structure that you see over here. Okay, now you remember? Fine. So as promised in the previous tutorial that I'd be elaborating on the stack pointer and the program counter registers. So this is exactly the video where I'm going to do so. Okay, so let's just start with the program counter register first. Okay, so here we are. Now in order to illustrate the role of the program counter register, so I just brought this program of 8-bit addition. Okay, as you all had seen previously. So now as you can see that our program basically starts from the memory location 0000. Okay, and well, before going into the function of the program counter, let me just emphasize over here that the 8085 microprocessor cannot store a program inside itself. Okay, instead it just employs external RAM chips in order to do so. So it just uses external RAM chips to store its programs. Okay, so we just use them to store the programs that are basically run on the 8085 microprocessor. Correct? You'll know that. Now whenever we are storing the programs in external RAM chips, we know that these RAM chips, well, they have certain arrays, okay, of 8-bit registers. So each of these arrays that you can see, all the horizontal lines, okay, there are numerous horizontal lines, and each of these lines, they just represent registers, or well, more precisely 8-bit registers. Since we can only use 8-bit such memory chips or such external RAM chips that have 8-bit registers, okay, with the 8085 microprocessor, since this also is an 8-bit microprocessor. Okay, so as I said that we just need to store our programs in the external RAM chips. So whenever the program is first stored onto such an external chip, then when the program is needed to be executed, the 8085 well fetches the instructions from the memory chips that are connected externally. Okay, so each of these 8-bit registers, they are just these registers are just they have a certain memory address. I mean, these 8-bit registers are they just addressed with a 16-bit memory address, okay, or a 16-bit hex address, okay, which we shall basically call the memory address, or the memory location, whatever it is. So these 16-bit memory addresses, they're just used to refer to each of the 8-bit registers that are just present in this way in the external memory chips or the external RAM chips. So the 8085 just reads the necessary opcodes and data one after the other from these external RAM chips. Okay, so let's say what happens is that I'm going to give you the true picture. Okay, so whenever you just power on an 8085 system, okay, like for example you can also take for example your 8085 trainer kit. So a system like that which employs an 8085 processor, microprocessor that is, whenever you just power it on, okay, by default the 8085 actually wakes up at the memory address 0000H. So as I said, the 8-bit registers in the external RAM chips are used to be referred to as with a 16-bit memory address. So this is the same as that. Okay, so it just wakes up at this address whenever the 8085 microprocessor is powered on. What do I mean by this statement? Well, by this statement I mean that the program counter register, which is of course a 16-bit register present within the 8085, the program counter register loads on a 16-bit data of 0000H, okay, in itself whenever you just power on the 8085 microprocessor. That's what I mean. And once the program counter loads itself with a 16-bit data, then that 16-bit data is just treated as a memory location, okay? Or more precisely, you can just call it a memory address. And from this particular memory address, the 8085 starts to fetch data. So if this memory address actually that is loaded onto the program counter register, if it actually corresponds to some 8-bit register of the external RAM chip being used with the 8085 system, then the 8085 microprocessor will fetch the data from that corresponding 8-bit register whose memory 16-bit memory address is loaded in the program counter. Okay, so basically we can say that the program counter register is basically a memory pointer register. Okay, and not only that, both the stack pointer and the program counter are well collectively referred to as memory pointer registers. Okay, they are more precisely referred to as memory pointer memory pointer registers, because they just store the location of the memory address or the corresponding memory location where the 8085 needs to search for data, opcodes, operands, whatever. So with this example, as I said, now you can also ask me a question that what if the program begins at some other address than the 0000H? What then? Now here the program that we illustrated, fortunately it just began from the address 0000H, okay? But like for example in few 8085 trainer kits, you'll see that the address starts from, let's say, 2000H, okay? So in those types of systems, what happens is that the memory starting from 0000H is just reserved for storing some other things, like for example compiler programs and other programs that are used to used for the proper functioning of the trainer kit and all. So those are different concepts. But even if the program starts from a different memory address, we can use the trainer kit to load this address into the program counter register. If you remember what you did at the lab, like after you just finished writing the program, you need to load the starting address of your program each time and then press the execution button. Okay, you remember that? Yeah, that's exactly what loads this starting address of your program into the program counter register. And that's where the program counter register begins counting steps. Yeah, exactly. I mean by that, counting steps. So this way we can summarize the functions of the program counter somewhat this way. That it's a 16-bit register, we all know that. But what's important is that it's 16-bit data content, okay? That is the 16-bit data that the program counter register basically stores. It just points to the memory location where from data needs to be fetched. So as I said, that if this 16-bit data that's contained in the program counter register, it can obviously represent any of the corresponding 16-bit memory address of any of the 8-bit registers of the external RAM chip in which the program is stored. Program or data is stored, and the 8085 will accesses the required program's opcodes or operand data from the 8-bit register whose 16-bit memory address is just loaded in the program counter. Okay, so this is what I mean by this point. And then the program counter register will increments its 16-bit content by 1 each time till the program ends. Okay, so as we can see that this program, I'm going to illustrate this point over here. As we can see that this program begins from the memory location 0000H. Okay, so you can see that. All right, so now what happens is that as soon as the content of the program counter register is 0000H, the 8085 begins to fetch the opcode and operands from the 8-bit register whose 16-bit memory address corresponds to 0000H. So let's say for example's sake we just take this beginning register over here, the topmost register over here, to have the memory location, I mean the address 0000H, and then the registers are well correspondingly numbered as 0001H, then 0002H, and so on. So when the 8085 is fetching the required hex codes the required opcodes and the operand data, whenever it's just fetching the opcode for the MVIC command, that is 0E, from this memory location 0000H, the program counter register, well, it increments itself by 1. Yep, there you go. And this way it just points, now its content, well, it just stores this, it just saves this incremented content, that is 0001H, in its 16-bit, in itself, or in its the 16-bit register, of course. So it just saves it, saves the incremented content right now, and this new incremented content is now used to point to the next memory location where from the next data is to be fetched. So now it points to the memory location where the data 00H is present. Okay, that is the operand for the MVIC opcode, right? And then whenever the 8085 is currently, let's say, fetching the data from the 0001H register, whenever it just fetching the required data from the 0001H 8-bit register of the external RAM chip, then again the content of the program counter register gets incremented, there you go, to 0002H. So now the program counter register content is 0002. So as you can see, this process just goes on and on. So whenever the 8085 is fetching the required data from one memory location, the content of the 16-bit content of the program counter register is immediately incremented, so that it is currently pointing to the immediate next memory location where from the data needs to be accessed by the 8085 microprocessor. Okay, so that's the role of the program counter. And now I'm going over to the stack pointer register. Okay, so here we are. Now, before going into details about the stack pointer, let me just tell you, let's just pull the discussion from where we left. So if we just once again take a look at the RAM structure of the 8085, well, we can see that the 8085 microprocessor has very little internal RAM. So it has very little internal RAM. Okay. And that's why it just uses the external RAM chips for storing its programs and data and all. Now, the data and the program that is stored in the external RAM chips, well, they are stored for a sufficiently longer time. But what if we need to increase the internal RAM capacity of the 8085? Now, let's say this program that we've just written over here for the 8-bit edition. Now this is fairly a simple program, but in case of more complex systems, we can basically have severely complex programs. For those, we might need certain we might need a lot many number of general purpose registers that is actually present in within the internal RAM of the 8085. What then? Well, there is a getaway. Well, due to this purpose, the concept of the stack is used in the 8085. Okay, so if we for example take this blue box over here as an external memory chip or an external RAM chip. Okay, so this is basically an external RAM chip, and here there are many number of 8-bit registers. Okay, so it just has a collection of 8-bit registers. Now what if we just reserve a space on the external RAM chip? Okay, let's say we reserve a certain amount of 8-bit registers on the external RAM chip to be used as general purpose registers. So this red square over here, it just indicates the reserved RAM space. Okay, so reserved RAM memory. Now this reserved RAM memory over here can be used as, can be used for temporary data storage. Okay, so this is exactly the idea behind what we're just trying to do over here. We're gonna use this RAM space, or the reserved RAM memory space, for temporary data storage, similar to what we, similar to the way in which we utilized the general purpose registers of the 8085, which is present within its inbuilt structure. So we're using it in the same way that we use the general purpose registers of the 8085. So this entire reserving of the RAM memory space to function for, to use it as, for temporary data storage, like the general purpose registers of the 8085. This entire process is actually, or the this reserved, this entire process, okay, better defined that way, is actually referred to as creating a stack. And this reserved RAM memory space, okay, is what is we call a stack. So we can basically define a stack as a collection of reserved external RAM chips, 8-bit registers. So if we just reserve some RAM memory space and use it for temporary data storage, then that is what we just call a stack. Okay, so now we can now the question basically comes that how do we create a stack? Now in order to create a stack, we need to supply a 16-bit memory location data to the stack pointer register. So the stack pointer register, so if we just take this as the stack pointer register, which is of course a 16-bit register. Okay, so now if we let's say our stack starts from the memory location, let's say 3000H. Okay, 3000H. Now note that I've just written down 3000H right at the bottom, but the stack starts from the top. Why did I do that? Now this is what you need to keep in mind, that we need to always declare the beginning of the stack at the highest available memory address. Okay, like in this case we have just let's say the 3000H is basically the highest available memory address in this case, so we just declare it over there. So now whenever we basically declare the stack from, let's say, from this address 3000H, we need to use a command known as LXISP, that is load the stack pointer with the 16-bit data and then supply the 16-bit data over here, which is the beginning of the stack. Okay, that is the location 3000H as we've just used over here. So now what happens is that now we're gonna have this 3000H, this memory location being loaded into the stack pointer register. Okay, there you go. Now the stack pointer register is storing the memory location 3000H, so we have just defined the beginning of the stack, and the data bytes that will be stored into the stack, okay, that will begin from the memory address. The storage of the data bytes, that's the data that you want to load in the stack, would begin at the address 2FFH. Okay, it will just begin from the address 2FFH. Now note that this memory address is actually one less than the memory address that is actually loaded in the stack pointer register. Okay, so we can basically conclude that the data storage begins at an address that is one less than the specified beginning of the stack area. Okay, so this is what you need to keep in mind. So first of all, we just declared the beginning of the stack, and now how do we store and then retrieve the data? Well, we can do it using certain instructions known as push and pop. Okay, now you always need to keep in mind that while using the statements push, the instruction push and pop, data in a stack area or in a stack memory space is always stored in pairs. So whenever let's say you are storing let's say this is a register B, okay, and this is a register C. Okay, so let's say B is storing a data byte of 2F and C is storing a data byte of let's say A5. Okay, and now, well, as you know that all the registers inside the 8085 inbuilt RAM, they are 8-bit registers only, and now you want to store these data from the inbuilt 8085 registers into the RAM space. Now what do? You are gonna write here, you're gonna use a push statement. Okay, so if you use the push statement, let's say push, you want to store the data of the register B. Fine, so you write push B, and then what happens is that, well, as you know that the data is going to be stored from the memory location 2FFH. So let's just say, for example, this register here represents the 2FFH location, and the other one just before it represents the location, well, 2FFEH. Okay, so now whenever you write push B, then what happens is that by the term push B, you don't actually mean to store the contents of the register B alone. Instead, you actually mean the BC register pair. Okay, so whichever name of the register that you're declaring after a push command, it is actually representing a register pair. So right now the B, by the command push B, you have already designated the B and C registers as a register pair. Okay, so what it's gonna do is that it's just gonna treat the data content, the byte present in, the byte of data present in register B as the higher order byte. Okay, so I'm gonna write that down over here. It's gonna treat this one as the higher order byte. Okay, and the byte present in, the data byte present in register C as the lower order data byte. Okay, so it's first going to store B's data content into the 2FFH register. So there goes, that is, it's going to store, well, 2F, and then it's going to store the register C's data content, that is the lower data byte. Okay, so that is A5. So there goes A5. So as you can see, as the data bytes are getting stored into the corresponding memory locations of the stack in pairs, the stack pointer register gets decremented each time. So whenever it is storing the data content of the register B at 2FFH, and then the content of the register C at, well, 2FFEH, then the stack pointer register, well, it gets, well, decremented by 2. Okay, since 2 of the memory locations have been used already in order to store the data bytes correspondingly, so the content of the new content of the stack pointer register right now is actually 2FFEH. Now this content of the stack pointer register indicates that the next two spaces, that is obviously 2FFD and 2FFC, is of course free for storage. Okay, so now that we've just stored the data, okay, now we need to retrieve them back once again. So what do? This time we use the pop statement, pop command. So we write pop and then give then specify the register pair. Once again, this is also going to be a register pair, and then we need to specify a name of a register pair where we want to copy the data that is stored, or just move the data that is stored in the corresponding registers of the stack area concerned. So if we write pop B, okay, then it just makes no difference because the data is already present in the B and C registers. Okay, but if we just write any different name of a register pair, like for example pop D, which actually, well, means the D and E register pairs. Okay, I'll just write it on the left. So it actually corresponds to the D and E register pairs over here. And let's say the D and E register pairs were empty. I mean, both the D and E registers were empty. And now whenever we write the pop D statement, then what happens is that the stack pointer register, well, it just gets incremented by 2, and the corresponding data stored in the register cells, in the registers, they just get transferred. So first of all, the data present at the highest occupied register, that is 2FFEH, okay, that contains A5, that is going to be transferred to the lower order register pair of the DE register pair. That is, it treats the register D as the higher order register. Okay, it just treats it as the higher order register, and it just treats the E as the higher, as the lower order register. Okay, so whenever we just declare a register pair, the hierarchy follows somewhat this way. So it first stores the A5 data into the E register. Okay, so there goes. And now the you can see that the 2FFE location is now empty. Okay, and also the stack pointer has been decremented by 1, so it is now pointing to 2FFF, indicating that the next two higher, in the next two spaces, that is 2FFE and 2FFD, are empty. And well, now the process isn't complete. Now we just transferred one of the data, and the other data of the register pair, that is 2F, will now be stored in the register D. There you go. So after that, once again we see that the location 2FFF has been cleared of the data that has been moved to the register D, and also the stack pointer register has been it has been incremented this time. So whenever we're just extracting the data from the stack pointer register, okay, that is popping out the data, then it's always incremented by 2, because we're just extracting a pair's data at a moment. And whenever we're just storing data into it, the locations, the stack pointer register gets decremented by 2. Okay, so this is exactly what happens. So we can see that the stack pointer register now is back at the starting address once again, that is 3000H. Okay, so this way we can just create a stack, store, and also retrieve information from the reserved memory space on an external RAM chip, and this way we can help execute very complex programs using the 8085 systems. So with that, we just come to the end of this tutorial, and gonna catch up with you all next in the forthcoming one. So till then, it's just gonna be a short goodbye for now, and thanks for watching.